Welcome to Ask and Learn.
This problem asks us to create graphs that represent flights between cities and then identify what type of graphs those are as a result of how they look. So where I started with this was summarizing the given information. So I just kind of made myself a visual out to the side. The way I set this up, this shows that there's 4 flights from Boston to Newark, 2 flights from Newark to Boston, and so forth. So there's lots of ways you could do that, but having that kind of summarized out to the side is going to help me a lot. I also went ahead and already set up all of my vertices. So when you're doing that, something you might want to think about when you're strategizing is thinking about what city has the most connections to the others. And in this case, that's Newark. So I kind of situated that in the middle to help me have space most of all as I'm looking to connect those. As we go through each part of this, there's subtle differences. And so you want to be looking for keywords in the problem. And as I went through those, I just kind of summarized each also. So hopefully that'll help us as we go. But let's go ahead and start with A. For part A, we wanted an edge between cities that have a flight between them in either direction was kind of a keyword there, telling us that direction does not matter. And so we want to connect each pair of cities that have flights between them. And this will be really simple. We see that Boston and Newark have one, Newark and Miami, Newark and Detroit, Newark and Washington, and then Miami and Washington. So that's all we have to do for that one. As you're looking into the table to help you classify, we can notice that this is an undirected graph. It didn't matter what direction these were going in. It doesn't have multiple edges between vertices because we were just looking to show the pairs, and there's no loops. So this is a simple graph. Moving on to part B, we want an edge in this case for each flight in either direction. So again, direction is not going to matter. This will be an undirected graph. But this time we want an edge representing each flight. So each flight is definitely a keyword here. As I'm looking kind of to my summarized information over here, I know that there's going to be 6 total flights between Boston and Newark. 5, 3, 5, and 1 between each of those pairs of cities. And so I'm just trying to fit in 6 edges between Boston and Newark, which might be a tight squeeze, but we're going to do our best. Something that you want to keep in mind as you're drawing these in, though, is that you do want to leave space between each of the edges so that you can tell that there are multiple lines there. So that is 5 total. Between Newark and Detroit, it's 3. Newark and Washington is 5. And then Miami and Washington just has 1. Again, try to make this as neat as you can, but at the end of the day, you need to have the total number of flights between each city, that number of edges, excuse me. So when we're looking to identify this, we have an undirected graph, but this time we have multiple edges between the vertices. We still don't have any loops, and so this one is called a multigraph. Multigraph. So as we go forward, part C had the exact same scenario as part B did, except now we're adding a sightseeing loop around Miami. So I'm just going to draw in what I had on that last slide. Hopefully a little bit quicker this time. Still trying to be neat though. So 6 between Newark and Boston. We need 5 here. 3, 5. That one, oops, that one between Miami and Washington still. But now we're adding in a loop, and of course on a graph that just looks like a circle. So something like that. So we have the same scenario when we're looking to classify again to undirected multiple edges between the vertices, but this time we do have loops. And so this one we will classify as a pseudo graph. And again, I'm using kind of the parameters that are given in that table for each of those. So you can look at those to help you as you're classifying. Part D says, in essence, that we need an edge from each origin city to each destination city. And so the key here is that direction does matter because it's telling us where we need to start and where we need to finish. Also, it doesn't say that we need one for each flight though. So that's telling us that we're not needing multiple edges, like showing each flight. So as I'm looking to my summarized information, I know that there's flights from Boston to Newark. So I need to show that. And we put these arrows in to show the direction. And then there's flights from Newark to Boston. And of course, arrows in the opposite direction this time. Same thing, Newark and Miami, they have flights in either direction. Same for Newark and Detroit. And Newark and Washington. Try your best to show which way these are pointing also. And last but not least, we have this one from Washington to Miami. We can put that arrow in. All right, so that's representing kind of all of the pairs again of origins and destinations this time. So as we look to classify, we have a directed graph because we included those arrows. It has, it looks like multiple edges, so don't be tricked here. This doesn't count as multiple edges in the sense of there's not multiple edges going in the same direction. So, and there's no loops. It's the last thing that we're checking for each of these. So in that sense, this is going to be a simple directed graph. Again, even though there's multiple edges between the vertices, they are not in the same direction. So not counting as kind of representing the same thing. Our very last one here is very similar to D, but now we want to say that there's an edge for each flight. So back to needing 6 between Boston and Newark. Draw these in. But the key here now is that the direction does matter. So we need to show which direction each of these are going in. So I'll just do this for now. I think that's still clear which way that's going. So if we're pointing this direction to pointing from Newark to Boston, between Newark and Miami, we'll have 5 total. And 3 are going from Newark to Miami. 2 are going from Miami to Newark. Go back just a second and fill these in. And this is the way we're going to proceed. So Newark to Detroit has one. Detroit to Newark has two. Newark to Washington is three. So Newark to Washington is three. The opposite direction is two. And finally, from Washington to Miami, we just have one. So as I'm drawing these arrows again, they're pointing in the direction that they're going. So hopefully that's pretty clear. And so as we're looking to classify this last one, we do have a directed graph. We have multiple edges between the vertices in the sense that even multiple and going in the same direction. And that's really the key here. There's no loops, obviously, but that's the defining characteristic is the multiple edges. So this one's going to be called a directed multigraph. You can see where the name came from. Directed and multiple edges. And we're all set.